Okay, so we've been looking at these power series expansions, and we've been playing around with picking the coefficients. Now we're going to do the reverse. We'll pick the function and see whether we can figure out what the coefficients are. So we're going to look at, as before, f of x equals a0. F of x is some function. This is the longhand way of writing it out. And we're going to pick for our function cosine of x. So the game is going to be, what are the a zeros that go with this particular function? And I'm going to go a little further because we're going to need it later. And how do we find the a zeros? Well, what do we know about the cosine? We know that the cosine of 0 is 1. Well, that's good. We also know that the cosine of x is equal to the cosine of minus x. That is, cosine is an even function. Well, the second fact suggests that all the x to the first, x cubes, x to the fifth, that those are all going to be 0. And the reason they're 0 is that they're odd powers, and we're looking for even powers. So we would think that the cosine only has even powers. We'll see if that's true or not. The other thing we know about the cosine, of course, is that the derivative of the cosine is the sine, actually minus the sine. And we know the value of that is at 0, which of course is 0. So we know the value of the cosine and its derivatives at 0. So let's go back to this equation and try using those facts. Let's plug in this equation, let's plug in x equals 0. On the left-hand side, we'd have the cosine of 0, which of course we know is 1. And on the right-hand side, we just get a 0 because all these other terms are going to be 0. They all involve an x or an x squared or an x cubed, and x is 0. So now we know a0. a0 is 1. Now what we're going to do is take the derivative of both sides of this equation and do this, and then plug in x equals 0 again. Derivative of the cos is minus the sine. On the right-hand side, we get a1, because the a0 term, which happens to be 1, the derivative of that is 0, plus 2a2x plus 3a3x squared plus 4a4x cubed plus 5a5x to the fourth, and we keep going. And now we're going to plug in x equals 0 into this equation. Let's see what happens. On the left-hand side, we get 0 because the sine of 0 is 0. And on the right-hand side, we get a1. So now we know a1 is 0, which is what we suspected. Let's do this one more time. Derivative of sine is cos, so we get minus cos of x equals 2a2 plus 6a3x plus 24a4x squared plus, 12a4x squared plus 20a5x cubed. So this is a 12. Now we plug in x equals 0 again, and we get minus 1, because the cosine of 0 is 1, equals 2a2, and the rest of the terms go away. That means that a2 is minus a half. So let's stop here and see if we can do some calculations. So we're going to try to use this formula. The formula we're going to use is cos x, which is carried out to the quadratic, to its second power, is 1 minus a half x squared, because the coefficient of x squared is minus a half, and the coefficient of x is 0. And the other things we'll just leave alone right now. We'll just assume that they're not important. And let's take a look at something like cosine of 0.1, and we'll evaluate both sides. So we're going to plug in x equals 0.1. Now 0.1, this has to be radians, of course. And by the way, 0.1 radians is about 5.7 degrees. So it's about 6 degrees, less than 6 degrees. So it's not a tiny angle. It's not a big angle. Now if you look up the value of cosine of 0.1 using your calculator or computer, I'll give you the value. And the value is 0.995004165, and it keeps going. On the right-hand side, I'll put a little question mark, see what we get. We get 1 minus a half of 0.01, because 0.1 squared is 0.01, which is 1 minus 0.005, which is 0.995. So we get the cosine accurate to 1, 2, 3, 4, 5 places, because there's looks like 2 zeros over there. That's pretty damn good. But it's not perfectly accurate. Of course, it can't be perfectly accurate because there are more terms. You'll notice that it's less, this value, 1 minus a half 0.1, 1 minus a half x squared, is less than the true value. So we'd expect the next term to be positive to bring it up closer to this. So let's calculate the next term. How are we going to do that? Well, we know that the cosine, going back to the previous equation, we know that the cosine minus the cosine of x, that was what we had before, is 2a2 plus 6a3x plus 12a4x squared plus 20a5x cubed plus, that was the equation we had before that we used to find a2. Now let's take the derivative of both sides. We're going to get the derivative of cos is minus the sine, so we get sine of x equals 6a3 plus 24a4x plus 60a5x squared, and we have more terms which we're not going to worry about. And again, we do the same trick. We evaluate both sides at 0. So this was already, I think, we did 1 derivative, 2 derivatives, 3 derivatives. I think this is the third derivative already. So now we're going to take and plug in x equals 0 on both sides, and we get sine of 0, which is of course equal to 0, is 6a3, which implies a3 is 0. And again, we expect that because a3 is in front of a x cubed term, and that's an odd power. So let's take this equation and do one more time. Derivative of sine is the cos, and we get 24a4 plus 120a5x, and there's more terms. And we evaluate both sides of this at 0, and we get 1 equals 24a sub 4, which implies a sub 4 is 1/24. So what do we got so far? We found a0, a1, a2, a3, and a4. By the way, a1 and a3 were both 0, which we suspect. And so now the polynomial has gotten longer, and we now have cosine of x is 1, which is the a0 term, minus a half x squared, because that's the a2 term was minus a half, and now we have plus 1/24 x to the 4th. And we can evaluate this at 0.1. Well, these first two pieces are just going to be 0.995. And And this piece, the next piece, of course, is 1/24 of 0.1 to the fourth, which is 0.995 plus 1/24 of 0.0001, which if you work it out is 0.995. 4166, which is awfully close to what we had before, which was the exact value, which is 0.995004165. So we've gotten it 1, 2, 3, 4, 5, 6, 7. It's accurate to 8 places. That's pretty impressive. Okay, so we're going to stop here, and we're going to do one more of these, and we'll do a general process to see how we can do this in general. If we have a function, not just a cosine function, but some arbitrary function, can we do the same trick by taking derivatives and matching up and getting a formula? And that's called the Maclaurin series or the Taylor series, and we'll do that in the next video.